Across the vast silence of space and the tangled geometry of the quantum world, an invisible structure vibrates, not with sound, but with possibility. Every beam of light, every flicker of gravity, every breath you've ever taken has passed through it, yet no one has ever seen it. And if it were to vanish, even for a moment, so would everything else. This is not science fiction. This is what physics now believes lies beneath everything we think is real. We've long believed the universe is made of things, solid objects, tiny particles, tangible matter. We imagined the world as a machine, built from gears too small to see. But as science carved deeper into nature's code, that illusion crumbled. What we found instead was a strange, ghost-like sea, fields, vast, continuous, omnipresent fields, not just around us but within us. We don't live on top of them, we live inside them. Fields aren't like matter. They have no edges, no shape, no boundary. They ripple, vibrate, and sometimes create particles. Everything, electrons, photons, quarks, isn't a thing in itself, but a tiny storm in an invisible ocean. Physics tells us these fields are more fundamental than the particles we see. They are the canvas, the particles, just the paint. But here's the catch. We've never observed a field directly. We see only the aftershocks, the particle, the energy, the flicker on a detector screen. The field itself remains unseen, untouchable. And yet, it may be the only thing that's actually real. So what are these fields? How do we know they exist? Can something we've never seen, never touched, never truly measured, be more real than everything else? This is the story of what holds the universe together, the unseen architecture behind every atom, every force, every law of nature. This is the mystery buried inside the silence between things. Are fields even real? You wake up in a world that feels solid. Your feet touch the floor. You grip a mug of coffee. You hear the sound of birds outside a window that keeps the cold at bay. Everything around you seems built from things, real things, tangible, firm, measurable, tables, trees, skin, bone. You know what's real because you can hold it, throw it, break it. But this sense of certainty, this visceral belief in solidness, isn't just incomplete, it's a lie. One so old, so embedded in the story of being human that we rarely question it, until physics did. Let's rewind to the world before that unraveling, a world of clarity and contact. In the Newtonian picture of reality, the universe was made of tiny, indestructible particles, atoms moving through absolute space, governed by simple laws. Every object, from a cannonball to a planet, could be described by its position and momentum. This mechanical vision of the universe became our default. Everything made sense. Everything was local, predictable, real. Touch was a transfer of forces between surfaces. Color was a property of reflected light. Heat was the agitation of microscopic atoms. And every one of those atoms, we believed, was a hard little billiard ball, spinning through space like celestial marbles. A grain of sand, billions of atoms. A human, billions of billions. The logic was comforting, the simplicity was seductive, but it was also wrong, because then came the cracks. Light, it turned out, didn't behave like a stream of particles. It diffracted, interfered, bent around corners, and in a devastating series of discoveries across the 19th and early 20th centuries, the comfortable world of classical physics began to collapse. Light was a wave, yes, but not a wave in air or water or any medium we could detect. It was a self-sustaining ripple in something else entirely. And then came the atom's own betrayal. We once imagined atoms as miniature solar systems, electrons orbiting a central nucleus like planets around a star. But this model crumbled too. Electrons don't orbit. They don't even have precise positions. They exist as probability clouds smeared across space like whispers. When we try to measure them, they jump. When we try to look at them, they change, the solidity vanished. And this is where the illusion breaks, because at the heart of everything we know lies nothing. A chair is atoms. Atoms are mostly empty space. Even the nucleus, the tiny dot at the center of the atom, is not truly solid. It's a seething swarm of quarks and gluons held together by forces we barely comprehend. And the deeper we look, the less we find. Reality dissolves into energy, probability, and uncertainty. So what then is the world actually made of? Modern physics offers a stunning, almost heretical answer. The world is not made of particles. It is made of fields. Invisible, omnipresent, vibrating fields. Not just one or two, but a separate field for every known particle. An electron field, a photon field, a quark field. These aren't things you find inside space. They are space, or rather, they define how space behaves. And particles, they're not little dots moving through these fields. They are the fields. Specifically, they are quantized ripples, excitations, tiny bursts of energy that emerge when a field is disturbed. In this view, an electron is not a speck flying through the void. It's a blip, a vibration, a wrinkle in an invisible fabric that extends across the universe. This idea is so radical, so unintuitive, that it still hasn't sunk into popular understanding. And yet it forms the bedrock of the most successful theory in physics, quantum field theory. QFT doesn't just describe how particles behave, it predicts them. Every particle interaction, every force, every shred of matter in the universe is governed by how these fields overlap, interfere, and ripple across the cosmic stage. And here's where it gets unsettling. These fields are everywhere, always, even in what we call empty space, even in the vacuum between galaxies, even inside your own body. They're not like air, something that can be moved or removed. They are the permanent backdrop of existence. Wherever you go, there they are. You are not just surrounded by them, you are made from them. But if they're everywhere and we can't see them, how do we know they exist? The answer lies in the way they betray their presence. We observe the consequences, the particles, the forces, the energy transfers, but never the fields themselves. They are invisible stagehands pulling the strings behind the scenes, and yet without them, the play falls apart. Imagine dropping a stone into a pond. You never see the water itself, not clearly, but you see the ripples. You see how the stone is slowed, how the surface bends, how the waves reflect the disturbance. The field is the pond, the particle is the ripple, and this changes everything. Because if what we experience as matter is just a ripple, then everything solid is an illusion. Not in the sense of being fake, but in the sense of being a temporary pattern in something deeper. When you press your hand against a wall, you're not making contact between two solid surfaces. You are experiencing the mutual repulsion of overlapping electron fields. You are feeling resistance between waves, not between things. This is the world you think you know, stripped bare. Your sense of touch is an illusion of proximity. Your sense of solidity is a side effect of forces between invisible, undetectable fields. And even your body, this mass of skin, muscle, and memory, is not a collection of stuff. It is a dynamic structure of field excitations held in place by rules you never see. So the world you know, it's not what it seems. Everything you call real, tables, thoughts, stars, yourself, is woven from something we've never seen and never touched, fields. And yet, we trust they're there, because everything we can see behaves as though they are. In the chapters ahead, we'll peel back the layers of this invisible architecture. We'll ask what fields really are, how we discovered them, and whether something so fundamental and yet so untouchable can be called real at all. But first, we have to understand what a field even is, and why physics is convinced they're the only reason anything exists. The word field doesn't sound dramatic. It's a gentle term, peaceful, familiar. It conjures images of wheat and wind or of football and farmhouses. But in physics, a field is something far stranger, far more fundamental. It is the most basic substance in existence, and yet it is not a substance at all. So let's ask the question plainly: what is a field? In science, a field is a way of assigning a value to every point in space. That's it. A number or a set of numbers that changes from place to place. It might represent temperature or pressure or the pull of gravity. You can think of it like a map. At every location, the field tells you something, what's happening there. A weather map, for example, is really just a set of fields. A temperature field, a wind field, a pressure field. The lines you see on the screen, the warm fronts, the arrows, they're all ways of visualizing invisible values spread across space. But these are just classical fields, macroscopic, tame, predictable. When physics peered deeper into the fabric of reality, those fields transformed. They became wild, quantum, strange. At the subatomic level, fields don't just describe what's happening in space, they are what's happening in space. Picture this. Imagine space itself as a still, invisible sea. Every inch of it is filled, not with water, but with potential, with possibility. And then, somewhere in that sea, a ripple appears. That ripple is a particle, an electron, a photon, a quark. It exists not as a marble rolling through space, but as a disturbance in a universal field. It is the field momentarily awakened. This was the breakthrough of quantum field theory. Instead of seeing particles as the building blocks of nature, physicists realized they were just the symptoms, tiny flickers on a much grander canvas. The electron isn't a thing moving through the electron field. It is a quantized vibration of the electron field. And that field exists everywhere, all the time, even in places where no electron is present. Every particle has its own field. There is a photon field, responsible for light, a quark field, for the particles that make up protons and neutrons, a Higgs field, which gives mass to all others, and each of these fields is layered over the same space you inhabit right now. They're not stacked like layers of a cake. They're stacked like radio signals, all occupying the same space, but operating on different frequencies. Here's another way to picture it, one that might feel more intuitive. Think back to an old-fashioned AM radio. You sit in your car and turn the dial. As you move from station to station, music appears, vanishes, and is replaced by static or talk radio. You're not moving through physical locations. The car doesn't change, the air doesn't change, but the signal, the frequency, does. Quantum fields are like that. Each one is a frequency embedded in the void. Particles appear when the field at a certain point resonates, when energy enters and the field begins to vibrate in just the right way. That vibration is the particle, and when it stops, the particle disappears. What's eerie is that these fields are not passive. They're not just sitting there waiting to be disturbed. They are always in motion. Even in a perfect vacuum, no particles, no energy, absolute zero, fields fluctuate, randomly, relentlessly. This is known as vacuum energy or zero-point energy, and it means that space is never truly empty. What we call nothing is in reality a seething froth of fields bubbling beneath perception. And it gets weirder, because in the quantum world, these fields aren't just numbers, they're operators, mathematical objects that don't have definite values until we measure them. They can exist in multiple states at once. They can interfere with each other. They can tunnel through barriers and pop particles in and out of existence. So when we say a field is everywhere, we don't just mean it fills space like air fills a room. We mean it defines space. It's part of the scaffolding of reality. Without the field, the particle cannot exist. Without the particle, we have no matter. And without matter, no stars, no planets, no people, no you. Now, to someone grounded in the physical world, someone who's worked with their hands, who understands machines, structures, weight, this can feel like a betrayal of common sense. How can something we can't see or touch be more real than the things we can? But science doesn't bow to intuition. It follows evidence. And every experiment, every test, every measurement we've ever made confirms that particles behave exactly as if they are ripples in invisible fields. There's a term physicists use, local field values. It refers to how the field behaves at a specific point in space and time. When you detect an electron, what you're really doing is sampling a local excitation in the electron field. When you feel warmth from the sun, that's the photon field in action. When your feet touch the ground, it's the interaction of the electron fields in your atoms and the ones in the Earth's surface. You're not colliding objects, you're colliding ripples. What's even more incredible is that these fields can't be turned off. There's no switch. The universe was born with them already in place. When the Big Bang exploded into being, these fields were there, already spread like invisible scaffolding through the newborn cosmos. They didn't appear later. They didn't form from other ingredients. They are the ingredients. So a field, in its purest definition, is a continuous, eternal, and universal entity. It is the quiet, undetectable hum that gives rise to everything else. And as you sit here, watching this video, on a screen made of electrons moving through silicon gates, you are experiencing the output of fields interacting with fields. Your eyes, your brain, your breath, your thoughts, they are all fluctuations, patterns in motion. You're not separate from the fields. You are the fields. A temporary concentration of ripples, tuned for a while into the shape of a human being. You are the universe, briefly aware of itself, made of the same invisible scaffolding that holds galaxies in place and whispers photons across the dark. And so we return to the question, are fields even real? If they are not, then nothing is. It began with an unsettling realization. The more we tried to define matter, the more precisely we tried to pin down the tiniest parts of nature, the more the solid world slipped through our fingers. Electrons refused to behave like marbles. Light refused to choose between wave and particle. Energy appeared where none should be. At the edge of certainty, physics cracked open, and something new began to shine through. The classical picture of physics had limits. Newton gave us gravity. Maxwell gave us the electromagnetic field. Einstein bent space-time itself. But it was the strange behavior of light and matter at the smallest scales that forced us to rewrite the very language of reality. The result was quantum mechanics, a theory as bizarre as it was accurate, a theory where particles could be in two places at once, where observation changed the observed, where probability replaced certainty. But even quantum mechanics wasn't enough. It was still a theory of particles, of things, of electrons, protons, photons, all zipping around like lottery balls guided by chance. And so for a while, physicists used this incomplete picture because it worked, sort of. But the real revolution was still brewing, one that would shake our idea of stuff to its core. Enter quantum field theory. This wasn't just a new theory, it was a new ontology. It didn't just describe how particles behaved. It proposed something deeper, that particles weren't fundamental at all, that they were merely events, blips, disturbances, vibrations, on a much more profound stage, that the universe was not made of particles, but of fields, continuous, invisible, ever-present fields. And the particles, just temporary excitations, like sparks on a wire. In this framework, an electron is no longer a point bouncing through space. It's a ripple in the electron field. Everywhere that field exists, an electron could emerge. If energy is added in just the right way, that ripple has a name, a mass, a charge. But it is not an object, it is a phenomenon. The same goes for the photon. You might imagine a beam of light as a stream of little particles. That's not entirely wrong, but it's incomplete. A photon is not a thing flying through space. It is a quantized pulse of the electromagnetic field, energy transferred through a wave that can't be divided except in whole packets. The light that fills your room right now, That's the electromagnetic field in motion, not flying objects, not particles with paths, just the field expressing itself. And this is the wildest part. Every particle we know is born of its own field. Quarks arise from the quark field, neutrinos from the neutrino field. The entire standard model of particle physics, the most accurate and successful description of reality ever devised, is really a set of rules about how these fields interact. And when fields interact, strange things happen. Imagine two fields overlapping in space. Their ripples meet, interfere, amplify, cancel. If the conditions are right, a new ripple is born, a new particle emerges. Matter is created from nothing more than the tension between invisible frameworks, and just as easily that ripple can fade away, collapsing back into the silent sea. This is not poetry. This is prediction. In colliders like the Large Hadron Collider at CERN, we slam particles together at near light speed, not to study the particles themselves, but to agitate the fields, to kick the calm vacuum into chaos and watch what emerges. And when it does, we detect the signatures, the echoes, the tracks, the brief flashes of energy, before it vanishes again. In 2012, one of these flashes confirmed something monumental, the Higgs boson. It wasn't just the discovery of a new particle, it was confirmation of the Higgs field, a field that gives mass to all others. Without it, the universe would be filled with massless particles zipping around at light speed. No atoms, no stars, no structure, no us. But what matters most is not the particle we saw, it's the field we didn't. Quantum field theory doesn't just model this reality, it defines it. It calculates with astonishing precision, predictions so accurate they've been confirmed to over 10 decimal places. When we measure the magnetic moment of the electron or the interaction between particles, the theory aligns with nature so precisely it borders on eerie, as if the math itself is the fabric of the universe. And yet, this framework, this stunning theory of everything we can see, is built entirely on things we can't. Fields we cannot isolate, ripples we cannot observe without destroying, phenomena that occur in dimensions of math we will never intuitively understand. For the older generation of physicists, those raised on the concrete world of forces and masses, this was almost a betrayal. Reality, it turned out, was not built from building blocks. It was woven from equations, from patterns, from ghostly interactions between invisible, untouchable fields. And here's what makes it all so strangely beautiful. These fields are eternal. They don't come and go. They don't have on-off switches. They are the stage upon which everything else happens. The particle that appears in your detector is not a visitor from elsewhere. It is an event, a local awakening, and when it fades, the field remains, unchanged, waiting. This is the quantum field revolution, a reframing of what the universe is made of. We thought we'd reached the bottom. We thought we had found the final marbles of nature. Instead, we discovered a shimmering tapestry, one that pulses beneath every atom, that holds the stars in place, that gives rise to everything we know, while remaining invisible to everything we are. And so the question grows louder. If the particles we see are only fleeting ripples, and the true reality lies beneath, then what is more real, the ripple or the sea? In the next section, we meet the most famous ripple of all, the one that gives mass to the others. A field so strange it took nearly 50 years to prove it existed, and when we did, it changed everything. The Higgs field, and the mystery of how something that cannot be seen makes everything we are. There's a silent question that haunts the foundation of physics. Why does anything weigh anything at all? Why aren't all the particles in the universe flying at the speed of light, massless, unbound, racing through the void with no anchor to slow them down? By all rights, they should be. For decades, this mystery sat like a crack in the wall of the standard model. Electrons had mass, so did quarks. But photons, particles of light, did not. Why? If these were all just excitations in fields, What made one field produce weightless ripples, while another produced matter heavy enough to build galaxies? The answer came in the 1960s, not from an experiment, but from theory. A group of physicists proposed something radical. What if space itself wasn't empty? What if, even in a perfect vacuum, there was an invisible field stretched across the entire cosmos, one that resisted motion, that pushed back when particles tried to move through it? They called it the Higgs field. Unlike other fields, the Higgs doesn't create force in the traditional sense. You can't feel it. You can't shield yourself from it. It's not radiating or pulsing or causing particles to attract or repel. It just is. A uniform, unchanging presence embedded into the very geometry of the universe, and its effect is subtle but profound. When certain particles move through this field, they interact with it. That interaction slows them down, it resists them, it gives them inertia. And in the language of physics, that resistance is what we call mass. It's not that the particles have mass because they're made of heavy stuff. They have mass because the Higgs field clings to them, like molasses, like gravity in a dream. You don't feel the Higgs field because you've never been without it. It's not a force that starts or stops. It's the stage upon which everything else plays out, but the effect is everywhere. Without it, electrons would be massless. They wouldn't bind to atoms. Atoms wouldn't form. Chemistry wouldn't exist. The stars wouldn't burn. The Earth wouldn't hold you. You would not be here. And yet, for nearly half a century, this field remained a theory, a necessary mathematical fix to a problem too strange to ignore, but unproven. Because while we could calculate its effects, we couldn't see the field itself. It was like gravity, its presence felt, its hands unseen, until July 4th, 2012. At CERN, in a collider buried beneath the Swiss-French border, protons were smashed together at energies never before achieved by humanity. And for a fraction of a second, something flickered into existence. A new particle, heavy, short-lived, exactly the mass predicted by the Higgs mechanism. It decayed almost instantly, but its signature was unmistakable. The Higgs boson had been found. It wasn't the field itself, but it was the proof, the ripple, the echo, the evidence that the field was there, like a single drop of rain in an otherwise invisible storm. And with that discovery, the standard model snapped into place. The missing piece, the last unknown particle in the theory, had been confirmed. But here's the strange part. Even now, with the Higgs boson observed, we still don't see the Higgs field. We only see what happens when it's disturbed. It remains, like all fields, invisible, eternal, fundamental.
So what kind of reality is this?
A field that gives mass to everything but can't be touched, can't be turned off, doesn't pulse, doesn't shine, and yet it holds the structure of the universe together. Without it, the cosmos would unravel into light and wind, no stars, no galaxies, no form. Imagine walking through fog that never moves, never lifts, but resists your every step. The fog is nowhere and everywhere. That's the Higgs field, an invisible viscosity in the vacuum of space. Every second of your life has played out inside it. Every moment of every story that ever happened took place against its resistance. But only certain particles feel it. Photons, for instance, are immune. That's why light has no rest mass, why it moves at the ultimate speed limit of the universe, why it can cross galaxies without tiring. The Higgs field lets it pass unimpeded, no drag, no mass, just momentum and energy. But electrons, quarks, W and Z bosons, they struggle. The field grips them, slows them, weighs them down. The more they interact with the field, the more massive they become. That's why the top quark, the heaviest known elementary particle, is so heavy. It couples intensely to the Higgs field. It's not just a property of the particle, it's a reflection of its relationship with the field. This turns our entire notion of mass inside out. Mass isn't a thing, it's a response. A particle's mass is not something it carries with it like a backpack. It's how hard the universe pushes back when the particle tries to move. The Higgs field is that push, that resistance. And so once again, we're left with something unsettling, something beautiful. The thing we experience most viscerally, weight, resistance, the solidity of the world, is not rooted in matter, but in interaction. Not in particles, but in a field we can't even detect without building billion-dollar machines and peering into trillionths of seconds. We think of ourselves as creatures of substance, but your body, your bones, your breath, they don't weigh anything on their own. They only weigh something because of the Higgs field. You are heavy because space itself pushes back against your particles. Mass isn't an attribute, it's a negotiation. So is the Higgs field real? To physicists, it's as real as any mountain or moon. It's the only explanation that fits the data. And with the discovery of the Higgs boson, it moved from theory to fact, at least as far as science can measure, but the deeper truth is still intangible. We have no idea why the field exists, or why it has the value it does, or what lies beneath it. Like so much else in physics, it is a solution that opens even bigger questions. Still, it answers one thing definitively. The universe has weight, not because it is made of heavy things, but because it floats in a sea that pulls on every step. A sea we didn't know was there, a field that never blinks and never lets go. In the next section, we'll go further into that darkness, the vacuum itself. We'll ask what space really is when you remove everything from it. No atoms, no light, no heat, just nothing. And we'll discover it isn't nothing at all. Close your eyes and imagine perfect emptiness. No air, no atoms, no dust, no light, not even heat. Just the infinite stillness of space stripped of everything. A pure vacuum. A cosmic nothing. For centuries, that's what we believed the void to be. A backdrop. A blank canvas, the stage on which reality performed, but never the performance itself. But the universe is stranger than that. Because when physics finally learned how to look closely enough, how to strip space down to its barest bones, it found something impossible. The vacuum isn't empty, it is alive. Quantum field theory tells us that even in a perfect vacuum, zero particles, zero energy, absolute stillness, fields remain. They never go away. They cannot be turned off. And more importantly, they cannot be kept quiet. These fields are restless. They shimmer, fluctuate, and whisper with energy, even when there's nothing there to trigger them. The universe, it turns out, cannot stop moving, even when there's nothing left to move. This irreducible jittering is called zero-point energy. It's not a metaphor or a quirk. It is real. It has consequences. Even at absolute zero, the lowest temperature possible, the fields still dance. Not because of heat, not because of motion, but because the uncertainty principle, the deep law of quantum reality, forbids complete stillness. A field with precisely zero energy and zero motion would have to violate the very structure of quantum mechanics, so the vacuum flickers. Virtual particles wink into and out of existence, energy surges and fades. The fabric of space becomes a storm, invisible and relentless. This isn't science fiction, it's measurable. Take the Casimir effect. It's a real, testable phenomenon named after Dutch physicist Hendrik Casimir, who predicted it in 1948. Place two uncharged parallel metal plates extremely close together, mere nanometers apart, in a vacuum. You might expect them to just sit there, untouched, unmoved, in empty space. But they don't. They move. They attract. Why? Because the space between the plates is so narrow that only certain wavelengths of the vacuum's quantum fluctuations can exist there. Outside the plates, the vacuum roars with full spectrum fluctuations. But between them, it's quieter, and this imbalance creates pressure, not from air, not from light, but from the vacuum itself. The plates are pushed together, not by something, but by the restless nothing in between. That's the quantum vacuum, a sea of invisible pressure, a reminder that space is never still, And it doesn't stop there. This same vacuum energy has implications on a cosmic scale. Some physicists believe it's responsible for the expansion of the universe itself. That dark energy, the unknown force driving galaxies apart, might be the large-scale effect of vacuum fluctuations we can't yet understand. In this view, the nothing between galaxies is not inert. It's alive, and it's pushing. It gets stranger. In certain high-energy conditions, like those in particle accelerators or in the early universe, these vacuum fluctuations can spike, birthing real particles. Not virtual, not fleeting, real matter pulled from the void. You can think of it as energy condensing into substance. The field becomes unstable, and reality bubbles up from what appeared to be nothing. This isn't just theoretical. In the phenomenon known as Hawking radiation, black holes, those perfect voids of gravity, are believed to evaporate slowly over time. How? Because of vacuum fluctuations at their event horizons. A particle-antiparticle pair emerges near the edge. One falls into the black hole. The other escapes. The black hole loses a sliver of energy. Over eons, enough of these moments can cause the entire black hole to dissolve into light. From the deepest void comes a slow, radiant death. Think about that. A black hole, the ultimate symbol of nothingness, slowly erased by the quantum tremors of the vacuum around it. So when we talk about nothing, we're not talking about absence. We're talking about the most energetic, structured, and mysterious form of reality we've ever encountered. You are surrounded by it right now. The space between your atoms, the distance between the stars. Every so-called void is a swarm of fields dancing just beneath perception. If you could somehow remove every atom, every speck of matter, every photon of light from your room, it wouldn't be empty. The fields would still be there, buzzing, unrelenting. In fact, you might say that space is never more itself than when it is completely empty. But here's the part that pushes it into the realm of the truly strange. We don't know what sets the energy of this vacuum, why it fluctuates the way it does, why it doesn't collapse under its own pressure, why it doesn't rip reality apart. Our best theories can calculate vacuum energy, and the result is terrifying. It's off by 120 orders of magnitude from what we observe in the real universe. The largest known discrepancy between theory and experiment in the history of science. It's called the vacuum catastrophe, and it tells us we're missing something huge. Maybe we don't understand fields as well as we think. Maybe what we call empty still contains hidden layers of structure. Or maybe our entire understanding of space, time, and energy is incomplete. But one thing is clear. The vacuum isn't passive. It's not an empty glass waiting to be filled. It's more like a vast ocean, invisible to the eye, whose tides and currents shape the very geometry of reality. The more we try to strip away the world and look for nothing, the more we find something lurking in the silence. So the question returns. If space is made of fields, and those fields never vanish, then what exactly is nothing? In the next section, we stop looking at what emerges from fields and begin asking what fields really are. What is this invisible structure that never goes away? Where did it come from? And how can something that's everywhere still feel like nothing at all? For most of history, we imagined reality as a collection of objects, things with shape, things with mass, things you could hold, weigh, measure, or break. First it was earth, fire, water, and air. Then atoms, then subatomic particles, electrons, protons, neutrons, and just when we thought we'd reached the bottom, it disappeared beneath our feet. What we found there was not smaller particles, it was fields. And the theory that emerged to describe them, quantum field theory or QFT, isn't just a new chapter in physics. It's a replacement for the book, a total rewrite of what it means for something to exist. In the framework of QFT, the universe is not made of particles moving through space. It's made of fields that permeate space, and the particles are simply the observable outcomes of how those fields behave. Picture the universe as a symphony, not a machine. The instruments are silent fields. The notes we hear, the particles, are vibrations played into existence. The music is reality. Each type of particle arises from a specific field. Electrons from the electron field, quarks from the quark field, photons from the electromagnetic field, gluons, W and Z bosons, Higgs bosons, all from their own corresponding fields. But these aren't separate layers stacked on top of space. They are space, interwoven, simultaneous, omnipresent. Quantum field theory is the mathematics of how these fields behave, how they fluctuate, and how their vibrations interact. And when they do, astonishing things happen. Energy can convert into particles. Particles can annihilate each other and vanish. Forces are carried not by magical action at a distance, but by field excitations. Particles flung across space as packets of influence. Every interaction, every attraction, every event in the universe is just a field talking to another field through local vibrations. Let's take the electromagnetic force as an example. In the classical picture, an electron creates an electric field around it. That field affects other charges nearby. But in quantum field theory, what's really happening is this. The electron is a disturbance in the electron field. It interacts with the electromagnetic field, which in turn sends out photons, the messengers of that force. These photons are quantized field ripples. They carry the information from one electron to another. They are not optional. They are required by the field equations. It's not that particles choose to interact. It's that fields are always communicating. And it doesn't stop there. When two particles collide, say at CERN, they're not two hard balls smashing together. They're two field excitations overlapping in space. When the energy is high enough, the collision disturbs nearby fields, which may then erupt with new ripples, new particles. These events are governed by QFT's rules, which are encoded in something called a Lagrangian, a kind of master equation that captures the relationships between all known fields. And the accuracy of these predictions is staggering. One of the most famous examples is the anomalous magnetic moment of the electron, a quantity that tells us how the electron's magnetic field slightly deviates from classical predictions. QFT calculates this value with such insane precision that when we measure it in a lab, the result matches theory to within 1 part in a trillion. That's like measuring the distance from Earth to the Moon within the width of a human hair. No theory in the history of science has ever predicted anything more precisely. But QFT isn't just a model, it's a reality engine. The standard model of particle physics, the culmination of over a century of experimentation, is built entirely on quantum fields. It describes 17 fundamental particles and their interactions through 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force. All of it, fields. Gravity, of course, is the outlier. We don't yet have a quantum field theory of gravity. General relativity describes gravity as the curvature of space-time, not as a force mediated by a particle. But physicists suspect there is a quantum gravitational field, one we haven't yet observed, mediated by a hypothetical particle called the graviton. If and when we find it, QFT may become a truly universal theory. And this raises an uncomfortable question. If QFT is so successful, why does it feel so strange? Because it doesn't resemble the world we see. We don't experience reality as ripples in invisible fields. We see chairs, we hear music, we feel warmth. And so for many, QFT feels like math without meaning, an abstract scaffolding beneath a world we prefer to think of in classical terms. But those terms are illusions. What we experience is just a convenient layer built on top of fields. Your sense of touch, a response to electromagnetic fields repelling each other. Your vision, interactions between photons and the field excitations in your retina. Your thoughts, electrochemical ripples through networks of ion channels, all governed by quantum rules. Everything you call real is just the macroscopic consequence of quantum fields interacting with each other across space and time. But here's the part that most viewers never hear. Quantum field theory isn't optional. It's not a philosophical interpretation, it's the foundation. If QFT didn't describe the universe correctly, your smartphone wouldn't work, lasers wouldn't fire, GPS wouldn't align, MRI machines wouldn't image, nuclear power wouldn't exist. The technology of the modern world is a byproduct of our partial understanding of quantum fields. And still, we haven't reached the bottom. QFT doesn't tell us why these fields exist, or why there are so many, or why some particles get mass and others don't. It doesn't explain dark matter, or dark energy, or why gravity resists quantization. What it does is model what we observe, brilliantly, but it leaves the deeper meaning untouched. So where does that leave us? We live in a reality that doesn't consist of things, but of fields. Fields that are never at rest. Fields that create the illusion of particles. Fields that communicate by tossing ripples across the void. Fields that define everything, but that we cannot see, cannot touch, and cannot turn off. We have replaced the atom with the equation, the object with the wave, the thing with the pattern. The universe, it seems, is not made of matter, it's made of math. And in the next section we'll confront how we know any of this. If we can't see fields, if we can't isolate them, if we can't bottle one and hold it in our hand, then what exactly is our proof? Because if we're going to accept that fields are more real than particles, we need to ask the next hard question. What do we actually see when we look for them? You've never seen a quantum field. No one has. Not in the way we see a tree or a mountain or a sunrise. Fields don't cast shadows. They don't glow. They don't have edges or surfaces. So how can we be so sure they exist? The answer is simple and profound. We watch what they do. In the world of physics, direct observation is a luxury. Most of what we know about the universe comes not from what we see, but from what we measure. And over the past century, quantum field theory has made prediction after prediction, precise, testable, astonishingly accurate. Each one confirmed not by speculation, but by experiment. And every confirmation points to the same invisible reality: fields. Take the electron. We can't see it, but we know it exists because of its effects. When you turn on a television or a particle accelerator or even a toaster, you're witnessing the behavior of the electron field. The static shock you feel when touching a doorknob? That's a rapid discharge of electric potential, energy rippling through the electromagnetic field. But the real magic happens when we look deeper. In 1947, physicists detected something unexpected. A tiny shift in the energy levels of the hydrogen atom. Just a slight bump, so small it took precise instruments to detect it. This became known as the Lamb shift, and it wasn't supposed to happen in the old quantum models. But quantum field theory predicted it perfectly. It showed that the fluctuation of the electromagnetic field, its restless zero-point energy, slightly altered the energy structure of the atom. Something invisible left a fingerprint, a whisper caught in the data. And then there's the anomalous magnetic moment of the electron, an awkward name for a stunning fact. When physicists measure how the electron interacts with magnetic fields, quantum field theory predicts a value so specific, so intricate, it stretches into 10 decimal places. When we build machines to measure that value, we find it matches. Exactly. Imagine predicting the circumference of the Earth to the thickness of a single strand of hair. That's the kind of precision we're talking about. It doesn't just suggest the presence of a field, it demands it. There's no other way to explain such mathematical perfection without the existence of something deeper guiding the behavior of particles. But let's leave the lab for a moment. Consider sunlight. When light from the sun hits your skin, it warms you. Not because little particles are colliding with your arm, but because the photon field is interacting with the electron field in your skin. That interaction creates energy. That energy becomes heat. What you feel as warmth is a handshake between two invisible fields. The experience is real. The mechanism is not visible. It's the same with every device you own. Your phone, your computer, your television. None of them would work without semiconductors, devices built entirely on quantum field principles. The design of these systems, the flow of electrons through silicon, the tunneling of particles through barriers, they all obey QFT. If fields weren't real, nothing we use would function. Every click, every beep, every glowing screen is proof. But the most dramatic evidence comes from high-energy physics, where we smash particles together and watch what happens. At places like CERN's Large Hadron Collider, we hurl protons at each other at near-light speed. When they collide, they don't break apart like bricks. They dissolve into energy, disturbing surrounding fields. For a fraction of a second, new particles appear, blips of mass, bursts of force. They leave tracks, heat, decay patterns. We never see the field itself, but we see what emerges when it's disturbed. Like watching a ripple pass through tall grass. You don't see the wind, but you see its path. That's how we found the Higgs boson, not by seeing it directly, but by measuring its debris, the unmistakable signature left behind when it decayed, just a whisper after being born. That event, that ripple, was enough to confirm the existence of an entire field, a field that had been hypothesized for decades, waiting patiently beneath every step we've ever taken. In short, we detect the undetectable by watching how reality changes when we push it. This is the heart of science, cause and effect. If something invisible consistently causes visible change, we have every reason to call it real. But what about fields we can't yet test? There are theories, like those involving dark matter or hypothetical fields beyond the standard model, that remain unconfirmed. But even here, the strategy is the same. We don't wait for the field to wave hello. We look for indirect influence. Does a galaxy rotate in a way that suggests extra mass? Does radiation bend near a star more than gravity alone can explain? Do particle decays occur at unexpected rates? The questions guide the detectors, and the detectors search for patterns that suggest more layers of reality waiting to be found. It's worth noting that many fields are already deeply accepted despite being forever invisible. We never see the gravitational field, we see what it does. Tides, orbits, falling apples. Einstein's theory of general relativity describes gravity as the curvature of space-time, but it too can be modeled as a field, a graviton field, if we ever find the particle associated with it. In fact, almost everything we take for granted, force, energy, motion, is more easily and accurately described by fields than by traditional objects. A thing is just a localized field event. The reality of a chair, or a spoon, or a star is the result of quadrillions of field interactions happening in tight, cooperative formation. Still, we're human. We like to see things, to touch them, to feel their weight. And fields don't give us that satisfaction. They are ghosts in the equations. But those ghosts explain everything else, everything solid, everything bright, everything warm. So when we ask, how do we know they're there? The answer is, look around. Your heart beats because of electrical fields controlled by the movement of ions. Your eyes see because photons excite rods and cones that communicate through synaptic fields. The memory you're forming right now, the curiosity you feel, the questions you're asking, they're all electrical events, unfolding in a 3-pound structure of quantum interacting matter called a brain. None of it works without fields. And none of it makes sense without accepting that what we see is just the echo of what we can't. In the next section, we'll step away from measurements and instruments and ask something older, something deeper. What does it mean for something to be real? Because if we can't see it and can't touch it and it lives entirely in math, then can we say it exists at all? Or have we reached the edge of meaning itself? What does it mean to be real?
It sounds like a simple question, until you ask it seriously, until you let it sink past common sense and into the foundations of physics, where nothing is what it seems and everything is made of something we can't touch. We live in a world where fields govern matter, probability governs particles, and observation affects reality. But if these fields, These unseen, untouchable, ever-present forces form the fabric of everything. How do we define their existence? Let's begin where most people begin, with the senses. We call something real if we can see it, touch it, measure it. A chair is real because you can sit in it. The sun is real because it warms your skin. A stone is real because you can hold it in your hand and feel its weight. But is that the limit of reality? The things that press against your fingertips?
Take air. You don't see it. You don't touch it in the traditional sense, but you know it's there because of wind, because of breath, because you die without it, so you call it real. Take gravity. You don't see the curve in space. You don't touch the field, but when you fall, you believe. We define reality not by appearance, but by consequence. If something shapes our world, if it has measurable effects, then it earns its place in the ledger of the real. Quantum fields qualify. They give rise to every particle, every atom, every force. They hold stars together and breathe structure into void. They're not a theory tacked onto reality, they are reality. The only catch is, we don't experience them directly. We experience their effects, their echoes, their footprints in a world we're built to perceive at the surface level. But if fields are invisible and untouchable, is it fair to call them real? Here's where physics touches philosophy. There are different schools of thought on what real even means. Realism says the universe exists independently of our minds, that there's a world out there, regardless of whether we observe it. In this view, fields exist whether or not we believe in them, whether or not we can see them. They are part of the machinery behind the curtain. Instrumentalism, on the other hand, argues that theories are just tools. They don't have to describe reality, they just have to make accurate predictions. It doesn't matter if fields exist, so long as the math works and the results match what we measure. Physicists often drift between the two. When the math is elegant, when the theory predicts something new and that prediction is later confirmed in a lab, it's tempting to believe in the thing behind the math. But belief is not the same as truth. And science, for all its clarity, doesn't require belief. It requires usefulness. So which is it? Are fields real, or are they just the best tool we have? Let's flip the question. Are particles real? We like to think so. But in quantum field theory, particles aren't fundamental. They're not self-contained things. They're ripples, temporary, localized disturbances in the field. If the field is the ocean, the particle is a wave crest. We see the crest, but the ocean is what made it. Does the wave exist independently from the water? Number. So maybe reality isn't a matter of things, but of relationships, of structures, of change. Maybe nothing is, only things that happen, events, ripples, patterns in the dark. That idea isn't new. Ancient philosophers like Heraclitus argued that everything is in flux, that stability is an illusion. In modern physics, that idea has come full circle. What we perceive as fixed, objects, mass, form, is just motion we've grown accustomed to. So let's return to the idea of reality itself. If something cannot be seen, cannot be touched, and can only be described mathematically, can it still be real? Well, can love be real? Can pain? Can time? These aren't objects. They aren't things we can hold. But they shape us. They govern us. We feel their consequences, their patterns, and so we accept them. Quantum fields are the same. Their existence isn't tied to visibility, it's tied to necessity. Remove the field and the universe stops working. Remove the field and the equations fall apart. Remove the field and you remove yourself. Even mathematics itself, arguably the purest, most intangible structure humanity has ever uncovered, raises this question. Is math invented or discovered? Are numbers real? Or are they just a language we use to describe something deeper? Quantum field theory suggests the fields themselves may be mathematical objects, not physical in the way a stone is physical, but more fundamental, more persistent, things that don't erode with time, things that don't rust or burn or decay, things that are. In that sense, fields may be more real than any object you've ever touched. Because the object will fade, the field remains. And so perhaps we must update our definition of reality. Maybe it's not what we see, but what persists. Not what we touch, but what gives rise to touch. Not what we observe, but what makes observation possible. Fields don't care if you believe in them. They don't need your senses. They are there whether you doubt or accept. And if you demand proof, they offer the same answer the universe has always given. Look closer. And when you do, you'll find something extraordinary. That reality isn't built from things, it's built from structure, from interactions, from invisible scaffolds that stretch across the universe, whispering mass into particles, tension into space, and existence into what would otherwise be nothing. So, yes, fields are real. And in the next section, we'll look at what that really means for you. Because if you are made of particles, and those particles are ripples in fields, then what exactly are you? You are not made of matter, not in the way you think. You are told that your body is made of atoms, carbon, oxygen, calcium, hydrogen, that those atoms form molecules and those molecules form cells, that you are, in essence, a biological machine composed of tiny building blocks. But beneath those blocks, beneath the atoms and electrons and protons, lies a different truth. One that quietly shatters the illusion of solidity and form. You are not made of particles, you are made of fields. Your atoms are structured fluctuations, waves of energy frozen into patterns by quantum law. The electrons in your blood are not objects circling nuclei. They are excitations in the electron field, rising into being and dissolving into silence in accordance with invisible symmetries. Your entire body is a standing wave, held in coherence by fields that never stop vibrating. When you touch something, when your fingertips press against another hand or the surface of a table, you are not making contact. The fields that constitute you are interacting with the fields that constitute everything else. Electrons repel electrons. Photon fields vibrate between atoms. There is no surface, no boundary, no skin. There is only field, resisting field. From a quantum perspective, you have never truly touched anything. But you have collided with everything. Inside you, the strong nuclear force binds the quark fields that form your protons and neutrons. Gluon fields lock those particles into place. The Higgs field clings to each one, granting mass like molasses grants drag. The electromagnetic field governs your nerves, your heartbeat, the tiny sparks that flash across synapses in your brain. These are not abstract concepts. These are the mechanisms of your existence. And all of them, every field, extends beyond you. You are not self-contained. The electron field inside your body is the same field that spans the cosmos. There is only one electron field, one Higgs field, one photon field. When we say your particles, we are speaking about local vibrations, temporary wrinkles in the universal fabric. What separates you from the stars is not substance, but structure. You are a pattern in an ocean of energy, a coherent resonance, a localized fluctuation in a universal field that has existed since the moment the universe was born. And that should be terrifying, but it's also sublime. Because if you are a ripple in the field, then so is everyone else, every human being, every animal, every cell, every thought. We are not made of separate matter. We are not built from separate stuff. We are the same field, dancing in different configurations. This means your body isn't a thing. It's a process, a momentary convergence of energy, a choreography of excitation. The particles in your hand today are not the ones from 10 years ago. Your body replaces itself. Cells die. Atoms disperse. But the pattern, the resonance, the you remains. What does that mean for consciousness? We don't know. But we know the brain is electrical, that neurons fire because of charges, that ions drift across membranes, that those charges are governed by fields. The thoughts you think, the memories you carry, are encoded in moving fields of potential. Your experience of the world is not detached from physics. It is physics. You are not observing the field. You are the field observing itself. That's the paradox. You are the machinery trying to understand its own design. The vibration wondering if it is real. A loop of awareness built from the same silence it's trying to study. And still, we insist on separateness, on identity, on control. But the field doesn't care about your name. It doesn't stop at the edge of your skin. There is no line between where you end and the rest of the universe begins. You are not in the field. You are not riding the field. You are the field. Just a local storm, just a flicker. But flickers matter, because somehow, in this sea of fluctuating fields, you became aware, you became conscious. The universe, through you, gained a mirror. And that changes everything. It means the field can question itself, can look inward, can imagine. And that brings us back to the strange and sacred question. If everything is field, and if you are a field, then what is the self? Not a soul, not a spark, but perhaps an echo, a resonance between many fields, tuned just right to create awareness, a moment where math becomes memory, where energy becomes emotion, where the silence of the vacuum folds into something that feels like life. It's not mystical, it's not religious, it's physics, but it's also poetry. You are not matter, you are music, a melody emerging from overlapping vibrations in invisible oceans, a song the universe is singing for a while before the waveform collapses back into stillness. And maybe that's enough, because it means you were never separate, never alone. You've always been part of something larger, something permanent. You are not a bag of atoms destined to rot and vanish. You are a temporary pattern in a set of eternal fields, and those fields do not vanish. Not really. In the next section, we'll ask whether these fields are the end of the road, if they truly are the bedrock of reality, or if they too are just ripples in something deeper. Because the universe has fooled us before, and the deeper we go, the stranger it gets. For decades, quantum field theory has reigned as the deepest truth we know. It underlies the standard model. It explains the behavior of matter, forces, energy, even the shape of space. It's passed every test, survived every challenge, delivered predictions with such pinpoint accuracy they seem to whisper the language of nature itself. But the universe doesn't owe us simplicity. And the question we now face is as old as science itself. Have we reached bedrock? Or is this still just the scaffolding? If fields are real, if everything we call matter is just the dance of energy across invisible frameworks, then we have to ask, what are the fields themselves made of? What generates them? Why are there so many? Why do some particles couple to them while others pass through untouched? In other words, why these fields and why these laws? The standard model contains 17 fundamental particles and a handful of fields, but it isn't elegant, it isn't complete. It requires dozens of parameters, masses, charges, coupling strengths, just input by hand. There's no deeper reason why the top quark is so heavy or why neutrinos are so light. No obvious symmetry that explains why the Higgs field exists at the strength it does. We can measure these numbers, but we don't understand them. Physicists call this fine-tuning. The suspicion that the universe's most basic settings feel too arbitrary, too perfectly balanced, and that's a clue. A whisper that perhaps fields aren't the end of the story, but the middle. Some theories go further. String theory, for example, proposes that what we call particles, and by extension the fields that give rise to them, are not fundamental at all. They are emergent, tiny vibrating strings of energy flickering through higher dimensional space. In this view, the electron is not an irreducible point, but a one-dimensional loop. Different modes of vibration give rise to different particles, just as different frequencies on a violin string produce different notes, and what we call fields in our three-dimensional world might be the projection of deeper geometries from higher dimensional space. Fields would still be real, but not fundamental. They would be shadows, the tip of the iceberg. Other theories, like loop quantum gravity, attempt to go beyond even that. They suggest that space-time itself, what the fields are said to exist in, may be quantized, made of discrete, indivisible chunks. If that's true, then fields aren't continuous fabrics. They're built atop a grainy, foamy structure of space-time. The ocean, it turns out, may be made of molecules. And then there are even bolder ideas, that fields may be computational, that the entire universe is a vast quantum simulation, an unfolding of mathematical information. In this framework, fields wouldn't be stuff at all, they'd be instructions, the illusion of continuity woven from discrete logic, like pixels on a screen appearing smooth from far away. Is this science fiction? Maybe. But every layer of physics we've ever discovered was once thought absurd. Atoms were once fiction. So were quarks. So was the idea of an invisible field that grants mass to matter. Each time we thought we'd reached the bottom, nature pulled the floor away again. It may do so again. There's another problem. One we've already glimpsed. Quantum field theory doesn't include gravity. It works for the small. It works for the strong. It governs everything inside atoms and accelerators, but gravity, the force that bends light, warps time, and holds galaxies together, lives in a different domain. It's explained by general relativity, Einstein's masterwork, which describes gravity not as a force, but as the curvature of space-time itself. But relativity and quantum field theory don't mix. Try to blend them, and the math breaks. You get infinities where you want predictions, contradictions where you want symmetry. Our two best theories, QFT and relativity, each masterfully explain different realms of the universe, but together they refuse to coexist. That's not a flaw in the universe, that's a flaw in us. It means there is something deeper we haven't yet found. A more fundamental framework that unites quantum fields and curved space-time. One theory to rule them all. We call it the theory of everything. We haven't found it yet, but if and when we do, it may redefine what we think a field even is. So, are fields the final layer? We don't know. They may be the most precise, most complete, most predictive structure we've ever uncovered, but they may also be temporary scaffolding, a mirage of permanence. One more story we tell ourselves to make the chaos legible, and even if they are fundamental, there's still the question of origin. Where did they come from? The Big Bang didn't just create matter, it created the conditions for fields to ripple. But why those fields? Why that configuration? Why this universe? Those are questions QFT cannot answer. So perhaps it's not a matter of whether fields are real, but whether reality itself has a bottom, or whether we live in an infinite descent, a never-ending unfolding of deeper and deeper patterns, each one giving rise to the one above, like roots beneath roots beneath roots, all vanishing into the darkness of the unknown. In the next section, we explore what happens when fields meet extremes, inside black holes, or at the birth of the universe, places where even fields may break down. Because if we want to find the next layer, we have to push the ones we know to their limits. There are places in the universe where even our best theories fall silent, places where the math screams, the answers vanish, and the very idea of a field starts to tremble. These are the boundaries, the fault lines, the seams where our understanding of reality splits open. The most famous of these is the black hole. From a distance, a black hole is simple, an object so dense that nothing, not even light, can escape. Space bends, time slows, gravity dominates. But as you approach the event horizon, the point of no return, the rules of the universe begin to bend, and beyond it, they shatter. At the heart of a black hole lies the singularity, a point where gravity becomes infinite, where matter is compressed into zero volume, where density and curvature explode beyond measure. And in that chaos, quantum field theory ceases to work. Why? Because QFT assumes a smooth, continuous backdrop of space and time. Fields ripple across this stage like waves on a pond. But near the singularity, the pond becomes a storm. Space is no longer smooth. Time no longer flows. The coordinates of the universe, the fabric itself, are ripped apart. There is no stable foundation on which to define a field. The mathematics spirals out of control. This isn't just a failure of calculations,
It's a fundamental breakdown in the model.
when we try to describe what happens to fields inside a black hole, how particles behave, how forces act, we get answers that don't make sense. We get infinities, we get paradoxes, and nature doesn't tolerate paradox for long. One of the most haunting is the black hole information paradox. When something falls into a black hole, a book, a star, a person, what happens to the information that described it? In quantum field theory, information is never truly lost. Particles may transform, systems may evolve, but the underlying information is preserved. That's a sacred law. But in a black hole, it seems to vanish. Evaporated, perhaps, through Hawking radiation. But the particles that escape carry no memory of what fell in. It's like burning an encyclopedia and expecting the smoke to recite the text. The radiation is random. The information, gone. If true, this would violate one of the core principles of quantum theory, and that suggests something deeper, that our framework, our understanding of fields and space and time, is incomplete. Now let's go the other way, not into a black hole, but back to the very beginning. The Big Bang, another singularity, another place where our equations dissolve. Just like with black holes, the Big Bang was a point of infinite density, infinite temperature, and infinitesimal size. All the fields of the standard model, electromagnetic, weak, strong Higgs, were crammed into a singularity smaller than a proton. There, the usual separation between forces vanished. The fields likely unified, then broke apart as the universe expanded and cooled. But our equations can't describe that unification. Quantum field theory can model what happens after the first instant, after the fields begin to decouple, after symmetry breaks and particles condense, but it cannot describe before. It cannot describe at. There is no quantum field theory of the singularity itself. It's not just that we don't have the math. It's that we may not have the language, because singularities, whether in black holes or the Big Bang, aren't just strange locations in space. They're signs, clues that we've reached the limit of our current understanding. They tell us that fields, as powerful as they are, may not be the bedrock, that something deeper lies beyond. Even in less extreme situations, quantum fields show signs of stress. In highly curved spacetimes, in expanding universes, in the presence of strong gravitational fields. QFT gives us answers, yes, but they come wrapped in assumptions. Assumptions about space being fixed, about time being linear, about energy being conserved, assumptions that begin to crack under pressure. And so we're forced to admit it. There are places we cannot yet go, not because we lack imagination, but because our tools, though powerful, are incomplete. That's why physicists chase a new theory, a theory that blends QFT and general relativity into a single seamless framework, a quantum theory of gravity, a new foundation beneath the fields, one that doesn't shatter at the singularity, one that doesn't break down where the old world ends. What would such a theory look like? We don't know. String theory, loop quantum gravity, causal set theory. Some have promise. All are incomplete. None are confirmed. But what they share is a recognition that fields alone are not enough. That at the deepest level, reality may be made not of waves or particles, but of something stranger, something we haven't named yet. And yet, the fields still work. Here, in this moment, on this side of the horizon, they give us the universe we know. The stars still burn, the atoms still hold, the forces still bind. Even if the edges are frayed, the center holds. And that's a reminder that the end of understanding is not the end of truth. That just because a theory breaks doesn't mean it wasn't real. It just means there's more. In the next section, we'll explore what that more might look like. Not in equations or experiments, but in thought, in speculation, in wonder. Because if we're just ripples in a sea of fields, and those fields might themselves be built on something deeper, Then the question becomes, what is the universe really made of? What lies beneath the fields? It's a question that drips with danger. Because up to this point, everything we've explored has been rooted in evidence, tested, measured, confirmed. Fields aren't a guess. They're a framework, a bedrock. But even the strongest bedrock invites the same suspicion. What's holding it up? There's no answer, not yet. But there are theories, whispers, mathematical hints in the dark. Let's begin with the most provocative idea, emergence. In this view, fields aren't truly fundamental. They're a phase, a macroscopic consequence of deeper laws we don't yet understand. Just like water is made of molecules, which are made of atoms, which are made of quarks and electrons, maybe fields themselves are made of something else, something smaller or simpler or less. Some physicists believe space and time themselves may be emergent, that our familiar three dimensions, plus time, aren't basic features of the cosmos, but consequences of deeper quantum information processing. That somewhere beneath the fields are qubits, the fundamental units of information. And that everything we experience, particles, forces, even causality, arises from their entanglement and arrangement. In this model, fields are like weather patterns, visible, powerful, structured, but ultimately made of microscopic, invisible interactions. It's not metaphor, it's math. And some researchers think this is where gravity comes in. That space curves not because of mass, but because of the way information is distributed and flows between entangled systems. This leads us to ideas like holography. According to the holographic principle, the universe may be like a projection, where everything that happens inside space is encoded on a lower dimensional surface. Think of a hologram etched into glass. The image you see in 3 dimensions is real to your eyes, but all the information exists on a flat 2-dimensional plate. Applied to physics, this would mean that fields themselves aren't inside the universe, but are projections, emergent patterns of data encoded at the edge of space-time. It sounds absurd. And yet versions of this principle appear in quantum gravity theories, in black hole physics, in string theory, and in certain toy universes we can simulate mathematically. It works. Reality becomes a holographic display. The fields we measure, the particles we call real, are merely shadows of deeper patterns etched beyond our view. There are other hints. Take the vacuum energy of quantum field theory. Our equations say it should be enormous, so dense it would rip the universe apart. But what we observe is almost nothing. Why? Some suggest a balancing act is happening. That positive and negative contributions to the vacuum nearly cancel. That what we call empty space is not empty, but exquisitely balanced, a consequence of something even more fundamental arranging the fields just so. Or take entanglement. 2 particles, separated by light years, can remain connected instantaneously. That's not a field interaction. It's something deeper. And some physicists believe this strange connection is the true thread of the cosmos. That space-time itself might be built from entanglement. That geometry, the shape of reality, is just a way of describing the network of quantum relationships at the foundation of everything. In this view, fields are like vibrations on a spider's web. Real, yes. Predictable, yes. But the web, the thing that makes the vibration possible, remains unseen, and maybe it always will. That's the paradox at the heart of all deep science. The better we understand reality, the more clearly we see how little we understand. Fields explain everything, until they don't. And in those gaps, in those edges where equations crack and mysteries rise, the next layer begins to whisper. So what might lie beneath the fields? Maybe a discrete digital fabric. Quantum cellular automata, rules that flip on and off, evolve through time and from which all physics emerges. A cosmic computer. Maybe vibrating strings, higher dimensional loops that weave the particles and forces into being. Maybe nothing. Maybe fields are the bottom. Maybe the universe is the way it is because it just is. No turtles all the way down. No answers beneath the answers, just structure, waiting to be explored. Or maybe the question itself is wrong. Maybe there is no beneath. Maybe fields are not built from smaller parts, but from principles, symmetries, conservation laws, invariances, ideas that don't occupy space, but define it. And from these principles arise fields. And from fields, particles. And from particles, us. If that's true, then the universe isn't built from things, it's built from truths. And that might be the most unsettling idea of all. That what lies beneath the fields is not a substance, but a logic, an architecture of thought so deep and so perfect, it becomes indistinguishable from reality itself. In the next section, we'll ask what all this means, not for physics, but for perception.
Because if the universe is built from fields, and we are built from fields, and even the laws beneath them may be mathematical,
then what is the difference between simulation and reality? And are we already living inside both? At some point, the lines begin to blur. We've seen that everything around you, everything you touch, hear, see, believe, is born from invisible fields. That the particles making up your body are not things, but events. That space is not empty, but alive with trembling structures. That even time itself may emerge from quantum entanglement and relationships beyond your senses. So here's the question. If reality is a dynamic network of fields, governed by rules, structured by symmetries and playing out like an evolving algorithm, what's the difference between that and a simulation? It's a question once reserved for science fiction, but not anymore. Because the deeper physics goes, the more it starts to resemble code, not metaphorically, literally. We see information at the core of black hole physics. We see entanglement giving rise to space-time itself. We see the universe behaving not like a solid object, but like a computation, a sequence of changes governed by logic, not substance. And so the question echoes through philosophy and physics alike. Are we living in a simulation? Not in the sense of a video game created by aliens, not a desktop universe running on someone's hard drive, but in a deeper, stranger sense, one where reality itself is indistinguishable from simulation because it is made of logic, not material, information, not substance. If fields are all there is, and fields behave according to precise mathematical laws, then the universe behaves like a system executing a program. Inputs, rules, outputs, repetition, variation, evolution. In this view, the entire cosmos is the unfolding of an initial condition, an algorithm that began with the Big Bang and has never stopped running. Every star, every galaxy, every thought in your mind, all the result of local field interactions propagating across a grand computational structure. That doesn't mean we're fake. It means the distinction between simulation and reality may be irrelevant. Because the fields don't care, they behave the way they behave. Whether you call it physics or code is just a matter of perspective. In fact, there's growing belief among physicists that information, not matter, not energy, not space, is the most fundamental entity in the universe, that every field is just a way of encoding how information flows and interacts. Black holes provide a powerful clue. They're the most extreme laboratories of physics. And yet when something falls into a black hole, the information about it, the total quantum description, doesn't vanish. It's smeared across the event horizon, encoded, preserved. That's what the holographic principle suggests. The entire volume of space may be nothing more than the projection of information stored on a surface. That's not metaphor, it's math. And if space itself is a projection, then what we call here may be no more fundamental than the pixels on a screen. Real, yes, but emergent, derived, computed. Even your perception, the feeling of being you right now, is an emergent pattern in field interactions. Your memories, emotions, sensations, they are information encoded in electrochemical pulses. Your awareness is a recursive field structure reflecting on itself, an interface, not an origin. And here's the twist. That doesn't make it meaningless. It makes it astonishing, because it means the universe is not a cold, lifeless machine. It's a story, told through information by fields across space-time. It means that everything matters, because everything is encoded, everything is traceable. Even the smallest vibration in the vacuum contributes to the whole. You are not a player inside a game. You are the process of the game. You are the field, writing and rewriting itself with every breath. And if this is a simulation, then it's the most complete simulation imaginable. One that is real because it contains everything: joy, pain, beauty, death. It includes suffering. It includes love. It includes the ability to question itself, which may be the highest form of reality there is. So maybe the simulation question is the wrong question, because the fields don't simulate reality. They are reality. They are the system, the architecture, the canvas and the paint. And you, your story, your body, your mind, are a recursive moment in that unfolding logic. In a universe like that, nothing is fake, only emergent. And the final question becomes, emergent from what? In the next and final section, we step back. We ask what all of this means, not for science, not for theory, but for us. If you are a field and the universe is a field, and everything you've ever known is a ripple in this infinite fabric, then what does it mean to be alive? You are not a thing. You are not an object in space. You are not a body that contains thoughts. You are a field, alive, flickering, momentarily ordered into the shape of a person. The story of physics has always been a story of unraveling illusions. First, it told us Earth wasn't the center of the universe. Then it told us the atom wasn't solid. Then it told us matter wasn't matter. That particles were not particles. That form was not form. That what we took to be objects were actually interactions. That what we thought was empty was full. And now, it whispers one final revelation. You are not made of stuff. You are made of patterns in a field. The difference is everything, because stuff breaks, stuff fades, stuff is gone when it's gone. But patterns persist. They echo, they reappear, they ripple outward, entangled with everything they've touched. You, this person you are right now, are a vibration in fields that stretch across the entire universe. Your mass comes from your dance with the Higgs field. Your warmth is a glow from the photon field. Your heartbeat is a rhythm in the electromagnetic field. And your very being is the orchestration of quantum states, coordinated just long enough to become aware of themselves. You are the field watching itself flicker. You are the universe watching itself briefly, through eyes made of light and gravity. And the story doesn't stop when you do, because the fields don't vanish, they reshape, they redistribute. Your pattern may dissolve, but not into nothing, into everything. Back into the sea of fields, into the quiet hum beneath all form, into the same structure that built stars and oceans and music and memory. You never left the field, you only became distinct. For a while. That's what it means to be alive in this universe, not to own a body, but to be a moment of coherence in a universe of chaos. A moment where reality became local, specific, personal, and then let go. But what you are does not end, because the fields continue, and what you were becomes part of what will be. That is not metaphor, that is physics. The carbon in your bones was forged in stars. The particles in your eyes are older than Earth, and when your pattern unravels, those same particles will ripple outward into new stars, new systems, new chances for the field to know itself again. So when you look at the night sky, know this. You are not under the stars. You are of them, made from their atoms, shaped by their forces, crunched from their gravity, illuminated by their photons. And when you die, you will not fall into nothing. You will fall back into everything. That's the legacy of a field. It doesn't end. It transforms. And so the story ends where it began, in the void. Only now we know the void isn't empty. It's alive, full of fields, full of possibility, full of you. And the next time you feel small, remember this. You are not small. You are vast. You are a fluctuation in the most elegant, eternal structure we've ever found, and for one breathtaking moment, you became aware. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.